Hello everyone and welcome to Physics 220 here at Grantham University. This is week 4 where we're going to look at momentum and rotational motion. So momentum, which is defined as mv or P equals mv, is the mass times velocity. The units of momentum are simply kilogram meter per second squares. It turns out there are no special units here, unlike forces that have newtons and energies that have joules. Newton discovered that there's also a relationship between the momentum of a system and the external forces, such that any external forces on a system produce a change in momentum over change in time. What that really is another way to write Newton's second law of motion in terms of momentum. Now, what would you expect to happen if all the external forces were zero? Well, if you set delta P over delta T equals 0, you can multiply both sides by delta T and you get 0 equals delta P, which means that the initial momentum equals the final, or the momentum is conserved. Now it's that fact right there that so many people use momentum. It is a vector quantity because the product of a scalar and a vector is a vector. So it's another physical property that's conserved in the system. Velocities are not conserved, but momentum is, which is another reason people like to use this. So it gives us yet another tool to solve complicated problems and situations in physics. So now that we have a little bit of a better understanding of the basics of momentum, let's look at an example. So a 3,800 kilogram open rail car coasts along with a constant speed of 8.6 meters per second on a level track. Snow begins to fall vertically and fills the car at a rate of 3.5 kilograms per minute. Ignoring friction with the tracks, what is the speed of the car after 90 minutes? So momentum will be conserved in the horizontal direction. Okay, we're including both of those in the system. Let A represent the car and B represent the snow. For horizontal motion, VB for the snow equals 0 and VB prime equals VA prime, because once the snow is in the car, it's moving with the velocity of the car. Momentum conservation gives the following. The initial momentum has to equal the final, or MAVA, the mass of the car times the velocity of the car, equals the sum of the mass of the car and the snow times the velocity of both of them. That's important because since the car is filling up with the snow, it's almost as if you're adding mass and then the velocity is changing also. So then VA prime is the original momentum divided by the total mass afterwards, or MAVA divided by MA plus MB. So this gives 3,800 kilograms times 8.6 meters per second, that's the original momentum of the car, divided by, again, our 3,800 kilograms plus 3.5 kilograms per minute times 90 minutes. When you put those in a calculator and calculate it out, you see that the velocity of the car is 7.94 meters per second. Now, in a real situation, you may not see this because the car is probably not going down the tracks by itself. There's a train pulling it. What it means, though, is as the snow starts to build up on the train has to work harder and harder to keep that velocity, thus its momentum the same. But actually, the momentum will be increasing as the snow builds up. So that's why they make sure there's no extra on the top of the car after a set amount of time. So now we get to rotational motion and then how it connects to linear motion. Again, we see there are a lot of similarities to linear kinematics here. We replace distances, velocities, and accelerations with angles, angular velocities, and angular accelerations. There are also connections between the two physical quantities, and here's a table to compare them. So we have translational, rotational, and a connection between them. So in the translational we have x, rotation we have theta, and the connection is if you're moving on a circle of radius r, x equals r theta. So then we have v, in the rotational we have omega, and the connection is v equals r omega. Our translational acceleration a, and our rotational acceleration alpha, and a equals r alpha. Mass is equivalent in the rotational system is what's called the moment of inertia, I, and notice it's a function of the mass and the radius squared. I will point out that I varies for different solids, and there's a table in the book to help out with it. It's the translational quantity force and its rotational equivalent torque, and they relate by torque is Rf sine theta, where theta is the angle between the direction you're pushing the force and the force. We have our linear momentum we just learned about. There's also an angular momentum, and it's interesting here is you just replace the translational quantity with the rotational. So L equals the equivalent of m, which is I, and the equivalent of v, which is omega. Work can be done also. Again, you replace the translational with a rotational. Work is tau times theta, and even there's a Newton's second law, which is F equals ma. Instead, we have tau equals I alpha. Also, all of our kinematic equations work. Again, you substitute thetas for x, omegas for v, and alphas for a's. Okay, a little more on angular and circular motion here. The emphasis here is on the angular versus linear quantities. Angular velocity is delta theta over delta t, or the change in the angle over the change in time. The angular acceleration alpha is change in omega over change in time. Again, notice they're the same as the linear quantities, just switching the values. Again, note these are average values, but there's also a full set of rotational dynamic equations, nearly identical to the kinematic ones. And again, those are in the lecture. They can be also used here. Instead of angles here, degrees here, one mostly uses radians, where 180 degrees is pi radians. Radians are used since they are actually the ratios of two lengths, thus one can convert back to distances much easier.